Okay, here's example 3.5. Find the potential energy of a 1,000 kilogram car when it is on top of a 45-meter cliff. Okay, so potential energy, there are different forms of it, but potential energy is the energy that something has based on its position, where it is. And so, for example, suppose that we have a staircase. And we have a ball that can be in different levels of this staircase. Based on gravity, what we know is the higher up an object is, if it falls, it will eventually move faster than if it fell from a shorter distance, right? So like this height is much greater than this height here, right? So what we know is that when this ball hits the ground, it'll be moving faster when it hits the ground than this ball would here because it's so much closer to the ground, right? So now what we're going to do is we're going to talk about that in terms of energy. Potential energy is the energy based on position. And again, there are different types of potential energy, but one of the most common ones is gravitational. And it turns out the formula for that, you've already seen it. It's the same formula, really, that we use for work of moving an object against gravity. The amount of potential energy that an object has depends on its mass, the gravitational acceleration of the Earth, we know what that is, and its height. Okay? And this, essentially what we would argue later on is that once this object is moving, its potential energy is being converted into kinetic energy. So as it falls, it will have less and less potential energy and more kinetic energy. Okay, so the calculation, as I said, is just like it was for work. So now, potential energy, mgh, that would be 1,000 kilograms. This is a car, it's way up here. It's 45 meters up. G is 9.8 meters per second squared. And then you've got 45 meters. Okay. So it ends up being a pretty big number. 1,000 times 45 is 45,000 times another 10 is about 450,000. So I'm going to round it off actually to about 440. And that we would have kilojoules. I'm sorry, let me write it this way. 440,000, sorry. And then we would have kilograms, meters times meters, meters squared over second squared. And again, remember the unit kilogram meter squared per second squared, that's a joule. So this would be 440,000 kilojoules. Okay. Now, if I were to then say, wait a minute, let's make it, once we get up into the tens of thousands, we want to start, once we get up into the tens of thousands, we want to start using the prefix. I'm sorry, I accidentally put the kilo. I jumped the gun a little bit on that. It's 440,000 joules. So now if I move it over to the left 3 places, that becomes 440. And now I can replace this with kilo. We did that in the previous example, right? 440 kilojoules is how much potential energy this object has if it's at 45 meters high, okay? And again, if you wanted to move that object up to that 45 meters, the amount of work would be the same. It'd be 440 kilojoules. And that will lead us into the next topic, which is called the conservation of energy. The amount of work that we do to move that object is going to be equal to the amount of potential energy that that object has once you've got it up to the top, okay?